Hello, everyone. Thank you for Professor Huang's introduction. My name is Kevin Chen. I'm a co-chair of a Fast Interrupt Task Group. I'm also the senior architect at Andis Technology. Prior to Andis, I've been working in Silicon Valley at Advanced Micro Devices, AMD, designing CPUs. And also in the Silicon Valley, I also work in NVIDIA, doing GPU, graphic process unit. Back then, AI, artificial intelligence, is not so popular yet. And then I went to MStar, and then I joined as a system company, and then joined to Andis. So I have a perspective from both the CPU side, also from the system side. So today, representing technical committee, I would give you a brief update on what the status of current technical committee. First of all, we know that RISC-V is an open instruction set architecture. So when we say open, by definition, so all its instructions and features are openly discussed and defined by its members. So it's not like previously you have one company telling you what to do, and you just have to take it. So here's roughly the procedure. So if you have some great ideas, you are very welcome to propose to the technical committee, saying that you want to add a set of new instructions, say you want to create your own new extension. So the technical committee will review it, see if people besides you have interest. If enough people have interest, it will form a task group. And once the task group is formed, then the task group is responsible to come up with the detailed proposal. When you have a detailed proposal, a final proposal, it will then be ratified, basically approved by all member companies. So you can see the process is very democratic. So you come up with ideas, and you ask people joining for discussion, and then you finally approved by all the member companies. So let's focus on the task group. So as I previously described, task group is the main focus of the technical discussion. The committee will get the procedure and approval, but the core, the technical details, the hardware is discussed by task group. So it's usually run by a chair and a co-chair, and it's responsible to get the ideas from all the members in the task group and form a consensus. Since there are people all around the world, there are people in America, in Europe, in Asia, so there will be some regular meetings via internet, of course. And then or some task group, they prefer to use discussion threads in the web or going through using email. So this can take some time because when there are multiple parties, multiple companies all contributing, it takes a while to discuss and come up with a conclusion. However, even though it takes some work, but this open discussion actually is the best way to combine all the talents and expertise from different companies. So instead of limited by the view or the knowledge of one single company, you can actually collect all the expert opinions from different companies who has been in the industry for a long time, or even from competitors. Previous competing company, they can all contribute and come about with a joint solution. So therefore, you are all encouraged to find a task group you like, and join it to contribute your valuable ideas. So currently, there are many task groups. There are already 17 task groups formed, active task groups, and there are more coming. So all you have to do is log on to the webpage of a RISC-V Foundation, and you will list all the task groups currently active. And you can choose which task group you are interested. You can first joining and listening, and then you can join the discussion. And then eventually your ideas may become the official standard of the RISC-V instruction set architecture. So let's see what these 17 groups, because there are so many of them, so I will just briefly introduce each one of them, but we don't have time enough to talk about all the details. So first is a base ISA task group. So this defines all the basic instruction set. So currently, it's going through the ratification process. So, and will soon be voted by all member companies. So this is the last step of becoming official for the spec. Fast interrupt, which I'm in this task group, and I will introduce it briefly afterwards later. So it's focused on to generate a very low latency vector priority-based interrupt controllers. So it's ideal for MCU or real-time systems which require very fast, very low latency interrupts. And also for P extensions, the chair is my colleague Zhang Hua, who will be presented later in the session in the morning as well. You will define the packed SIMD DSP extension using integer register, not to be confused with vector register. It will use the simple integer register, so it's very packed and ideal for MCU or embedded applications. And you also define the compiler intrinsic functions for the high-level programming language. So so here's another privilege spec. So this defines the privilege mode, how the operating system, all the features for the operating system, and so on. And it was there even before the foundation. So you just ended, currently just ended its public review period. So here's the process. Once you have the final proposal, it has a 45 days of open review period, which will be sent to the public. People can look at it and see whether they have an opinion or question, and then eventually they will be voted. They have to answer all the questions, and then the member company will be voted on the final spec. That's called ratification. So they already passed the public review period and going into the ratification process. And software toolchain, our company and this also contribute a lot in this area. And since there are so many activities going on, there will be a dedicated session tomorrow just describing all the activity going on in the software toolchain. And vector extension. This is a very popular extension due to recent AI applications. And recently, it just released a draft spec of version 0.7. And processor trace. In order to do tracing, you want to come up with a standard hardware interface and packet format for all the vendors can agree on, one standard. A debug task group. So it's already ratified its spec now, and it's available on the web. And its errata is rolled into the ratified spec. And there are since security is so important these days, there are not one, but two task groups. There's trusted execution environment task group, and also cryptographic extension. So these two task groups are dedicated for security in RISC-V. So you can be assured that the RISC-V will be safe. So there's a bit manipulation, compliance task group to make sure that the CPUs from each vendor can work and talk to each other. Formal spec, we even have a formal specification to make sure things are correct. And J extension is for just-in-time compiled or interpreted optimization, memory model, and opcode space management. Because we have so many extensions, we want to make sure that the opcode space is not overlapped or have conflicts between different extensions. And finally, there's a SV128, which RISC-V is already looking ahead and defining a 128-bit virtual address space. And since I'm the co-chair of the fast interrupt group, and so I just would like to give you a brief update on the fast interrupt. So the spec is almost finished, but still has some detail to be finalized. So the goal is to come up with a very low latency interrupt control scheme. And we call it like a core local interrupt controller called CLIC. Its main features are it supports 4096 interrupt sources. So it can handle most of the applications pretty much. And it supports up to 256 priority levels. You don't have to implement all of this. Depending on how many you need, you can tailor to your applications. And also support automatic hardware preemptions. So priority will automate, the preemption will be, so high priority would take over low priority automatically. And lastly, also we have a feature called selective hardware vectoring. Since this is kind of new, so I'll talk about the selective hardware vectoring. So this is actually proposed by Andis. We proposed this architecture. This feature is because we want to let users to choose the behavior of each interrupt. So by choosing the behavior of each interrupt, you can actually optimize each interrupt and gain the benefits of both vectoring and non-vectoring interrupts. So what are the benefits? Say, take a hardware vector interrupt, for example. It's fast. Basically, it's fast. Hardware will take your reason and just dispatch it right away. So the latency will be only like 2 or 3 cycles. That's it. And but the downside of this is it has a slightly bigger code size. The reason is each interrupt has to save and restore its context on its own. On the other hand, like a non-vector interrupt, its advantage is it has a smaller code size because all interrupts share one copy of the same common code to save and restore its context. Because they are sharing one copy of common code, so its code size is smaller. However, since they are sharing, they all have to jump to the common code and come back to its own handling. So it's slower. So in order to optimize this, you can typically the best usage is select from your interrupt which one are critical, most timing critical. You can assign them to be vectors, and while the less not so critical interrupts, you can assign them to non-vector. This way, you can optimize for your interrupt latency response for the critical ones, while saving code size on the other ones, on the not so critical ones. Also, we have some additional optimizations. So to avoid creating new instructions, because we don't want to incur extra burden on the compiler, toolchain, and so on, so all our optimization use special controls. We only use special CSR, control and status registers. For example, we have a CSR, special CSR, to find the highest pending, the pending interrupt with the highest interrupt priority level. So this helps to improve the response of non-vector interrupts. So software can use this to do like, say, late arrival or tail chaining the popular one. You can implement all these features with this feature very quickly. Also, we also added a CSR to do conditionally swap the stack pointer based on the previous mode. And this is to help to speed up the OS when they transfer mode from user level to super user level. And also, we added a special CSR to conditionally swap the stack pointer based on interrupt level. This is useful for a real-time OS RTOS, because RTOS doesn't use all runs in the same previous mode, but you will based on the interrupt level and swap the interrupt between like interrupt and non-interrupt code. So this is a very quick update on the fast interrupt task group, and since the time is limited, so any questions? I think the question is how do you decide whether this special register exists or not in one processor or not, right? How do you determine whether one CPU supports it or not?
That's one. Another thing is, I think you must configure CINT before you use that, right? No?
Oh yeah, this hardware has to support this. Either you have it in hardware or not. So you have to configure it, yes.
Yeah, so I mean the way to configure that, suppose it's not patent specific, it must be standardized.
Yeah, so this goes through the, because of limited time, I didn't go through the details, but you follow the traditional convention. For example, like RISC-V has a PLIC, platform level interrupt controller and other click. So using the similar mode control, you can specify which mode you want. You can either select this local interrupt, support priority, or you can select PLIC or select the basic features. So it's follow the standard RISC-V way to configure it and select it. If the hardware supports it, then software can select it and use it. Thank you.